think I need to. Is it still going, right? It's live?
No, just want to
Oh,
double
you
check before you.
saw green.
Yeah, we're still good.
Okay, excellent. Okay.
You connect to reconnect or something?
I can. Maybe that'll do it. No, it's different. I'll give it that. Don't care about that.
Oh,
Yeah, there we go. That looks okay. Okay, and we'll maybe cover some things that people are familiar with, but it's always good to hear about validation, I think. And to emphasize that, again, a lot of what I'm going to talk about really is, some of it certainly stems from the work of the Richardsons, Jane and Dave Richardson at Duke, who've really pushed the idea of structure validation. And I think a lot of you are familiar with mole probity as a sort of source for doing that. So that's really their work. But this general theme here, which is, we construct models to explain experimental data. So we do that in science just generally. A lot of science is making some observations, then having a model, a theory that describes that, and making a model, and then validating that model. So we always have to ask ourselves whether the models that we make are correct, or as correct as they can be, given that there's uncertainty in what we measure. Typically, we don't measure something to infinite precision. So does our model fit with known data? Does it predict data? Or something you can measure? We often do this. We do a structure. From that, we might predict that a mutation would change something in our enzyme or our protein, and we make mutations, and then we measure that biochemically. Yeah? So that's sort of sensible things to do, but that's, in a sense, a validation. Does the model confirm prior knowledge? As I said, can we predict things? And I think maybe people are familiar with this idea. There's a distinction between accuracy and precision. Yeah? That accuracy talks about how right something is, and precision talks about how similar the models that we make given the data are. Because we can have things that like this, if there's a dartboard and we throw darts, and if the real answer is the center here, the bullseye, this is a set of models that are not very accurate because they're not near the answer. They're also very different, so they're not very precise. Yeah, so that's one extreme. The other end of that is things where we hit the bullseye every time. So we have models that are very precise, but also very accurate. Then there's things in between you can imagine where this is not a bad situation. This is really often what we have in reality in crystallography, I would say. We have actually fairly good accuracy, and that we're kind of close to the right answer. But, sometimes our precision is variable. What you want to avoid really is something like this, which is low accuracy but high precision. Because the high precision might fool you into thinking you've got something that's good, but you're actually a long way from the right answer. And when we think about experiments, there are errors, of course, and we can divide those into different kinds. So we get random errors, noise, when we do experiments, and they will have a certain impact. Often they impact the precision. Yeah, we can have models that fit noisy data equally well, but they'll be quite different. And we try to get around that in crystallography, for example, by doing lots of measurements. We do the same in cryo-EM, for example, collecting lots of pictures. Redundancy. That's expected in any experiment, typically noise. What you don't want, but you may anticipate, is systematic errors, so bias, where something about the experiment gives you data results that are systematically not correct in some way. And there are reasons why we might get that. the good thing about systematic error is you should be able to do the experiment again and get the same systematic bias. Yeah, so that's potentially one way to discover that. Systematic errors affect accuracy, though. Yeah? They'll point you in the wrong direction. Then finally, one may have gross errors where you make some very poor assumptions about what you're looking at, and those could lead to very bad results. And often you can, or maybe you can detect those as outliers. So you do an experiment, you solve a structure, the structure is completely inconsistent with every biochemical piece of data you have. I wouldn't personally assume that the biochemistry is wrong. It's very dangerous. I would look at the crystallography and wonder whether I've made a gross error, because that could be a sign of a serious issue. Okay, so just some general thoughts about errors, the impact on what we do, validation generally. So the question is, how do we know if we're doing a good thing in structural biology, let's say generally? Crystallography, but increasingly things like cryo-EM. So can we look at the pictures, right? These structures here. Is that first one on the left, is that a good structure? Yeah, no? Any feelings about it? Hopefully you'll tell me I can't tell, it's just a picture. Stop asking me a stupid question, Paul. Because this first one here is wrong. It was retracted. Or it was certainly retracted. I mean, I can't necessarily say it's wrong, but it was retracted, so it's clearly some issue. But it looks like a protein structure, so clearly just looking at the pictures is not good. The second one, again, looks like a structure, but there's some real evidence of fraud in this case, and there's something not wrong with this, not right with this structure. The one in the end, how do you think that is? Well, you just fall into the trap of thinking I'm going to say the same thing again. No, it's actually right. It's actually right. But if you look at it, it really has pretty poor geometry. So, you know, it's a right structure, but it doesn't fit all that we know about chemistry. And there's a reason for that, because it's a membrane protein solved at low resolution. So, you know, you might expect that, but as Pavel's shown you, there are things that we can do to try and improve chemistry, even when we have relatively poor data. And you may think, well, those are kind of things that people used to do. There are some prime examples before we had things like the free R factor. But in one of those structures I showed you on the left, you know, that was one of the structures that came from a retraction of a number of crystal structures that happened not that long ago, a few years ago. So mistakes can still happen. So don't assume that because crystallography has moved on and because we have these great pieces of software that you don't have to worry about getting things wrong, right? You should, all the time you should be asking yourself, is this the right thing? You know, that's what good science is about. Now, in practice, you're not likely to solve a structure incorrectly, I think. I would hope not anyway. But there are things that are more likely that you will encounter, both in terms of what you do and also in terms of what other people have put in the protein data bank. The most common thing you'll come up against, probably that's of some impact, is register errors, where people have got the sequence out of register by 1 or 2 residues. At lower resolution, it's very easy to do because if you look at loops, for example, at low resolution, because the density is smeared out a bit, they always look a bit shorter than they should be. So the temptation is to build too few residues in there. So you come in a bit short, you're out of register by 1 or 2, then somewhere along the line you happen to build a bit too long, then you get back in register, and it's all kind of okay in general, but there are places where there are things that are not quite right. So this happens. And there's an estimate there's about 1% of structures in the PDB have some kind of register error. And that's not a criticism really of people, it's just that, you know, it's difficult to do crystallography, even with the data and the tools that we have now. And this is just to mention that Tom and others developed some nice tools to try and remove bias to get better ways to interpret maps, so that, to try and avoid these problems of interpretation that lead to register errors. There are other things that you will see more or less frequently in the protein data bank, which you may do yourself. Sometimes people get the unit cells wrong or the wavelengths wrong. That should happen less and less frequently because synchrotron beamlines get better and better. We normally know sequences now because everything's sequenced to death. Yeah, so we're not normally trying to guess the sequence from the crystal structure, which is the way it used to be. Often, though, there are waters in the wrong place, too many put in. Maybe people have built waters instead of side chains and moved the side chain into the wrong place. Happens a lot. People often put, water instead of an iron, because sometimes it's difficult to tell. Maybe you have to do another experiment to figure it out. And then a lot of things that are a bit not so great in the protein data bank are small molecules, the ligands that we put in our structures. Somebody, I can't remember who said, but really macromolecular crystallography is not a good way to do small molecule structures, right? It's not really, there's a whole other technique for that. So I won't say much more about, maybe I'll say a bit more tomorrow about this in the tutorials, but really it goes back to talking about chemistry again, that crystallography is really chemistry, and small molecules, getting those right is about knowing some chemistry. So it's worth investing the time to make sure you understand the chemistry of what you're putting in there, especially if it's a new ligand that nobody's done before, because you can make a real mess of it. And these aren't the worst examples that one could find either. Okay, so what can one do to try and validate models in crystallography? There's a few global validators that you will often see reported in papers or even by the programs. You'll see things like R factors, the free R factor. I think everybody's familiar with that idea of cross-validation, taking some data out of the fit and using that as an independent assessment of what you're doing. We often report things like ideal deviations across the whole structure for angles and bonds. A very gross kind of measure of whether you're doing something really bad or not. So those are very important, but in general, what's going to be of more value to you in the details are these local validators. So does this side chain have some geometry problems in terms of bond lengths and bond angles? Is it a recognized rotamer? Is it in a sensible place in the Ramachandran plot? And we can also look at the local fit of a side chain to density. Yeah, and we can get a plot of how well does each side chain fit the density. So there's all kind of things that we can look at to try and make sure that what we're coming up with makes chemical sense. And I'll talk a little bit about some of those. So again, crystallographic measures, we have things like the free R factor, but then we can also look at this local fit of the model to the density. We just calculate a mask around a residue, look at the density values around that residue, and then compare those to the ideal density we'd calculate from the model. And ideally, those two would correlate quite well. And you can make that as a correlation. You can make it as an R factor. They're similar. They're related in some way. So that's a very useful thing. If you build something into your model and it has a very poor correlation with the map, there's something probably not quite right. Yeah, maybe that part of your model needs to move in some way. Let's think about geometry. So generally, things that are good for validation are things that have not been used in the optimization. That's the idea of the free R. We take some of the data out of the fit, so the model's never been forced to fit that data. Standard statistical approach. You can think about the same kind of thing for geometry. Generally, we don't try to force our models to fit the backbone distribution of proteins, what's called the Ramachandran distribution. When we do refinement, we don't impose values for the torsion angles along the main chain of a protein. So that's kind of a nice cross-validation. If we come up with a model at the end of the day that looks like it conforms to what we know about main chain geometry, then probably there's something good about that. And if it doesn't fit what we know about main chain geometry, maybe there's something bad. Well, just to be clear, what we're talking about are these two torsion angles, phi and psi, along the main chain of the protein. Yeah? And Ramachandran, years ago, theoretically actually really figured out that those should have some constraints because of geometry, that you couldn't have certain combinations of phi and psi for protein amino acids because they would clash into each other. Yeah? So there are places where there's steric hindrance. So that's kind of the classic Ramachandran plot here, where these points are all values for phi and psi, taken lots of residues from the protein data bank. So it's corresponding to beta strand and alpha helix, these two big peaks here. And this is a more sort of 310-like structure. And then there's a whole region here, for example, where you really don't expect to see anything because things would be hitting each other. It's really impossible to put something there.
So the hydrogens are considered in those kind of.
Well, these are just measured. These are extracted from protein data bank structures of high quality. But yes, if you're doing sort of theoretical calculations, you'd want to include hydrogens as well. And there is enough data now that you can actually divide these things out by some residue types, like proline, because it's a very unusual, different kind of residue, has a certain kind of distribution, as does glycine. And then there are some sort of correlations between residues as well. But if you come up with a model, and again, we don't force our models to fit this distribution. If we come up with a model that is consistent with this distribution, that's a nice cross-validation. So this is a model here. Is that good distribution? I think the red is probably a bit of a giveaway anyway, but yeah, this is an example where this model has a whole bunch of things in places where really statistically it's virtually impossible that something should be. So this is a model that one would look at and say, okay, I should be doing something different here in the process of refining this structure to actually make it better. This is clearly not chemically sensible. And you actually expect 98% plus of the residues should be consistent with this Ramachandran distribution, and a small percentage are likely to be, could be outliers, less than 1%. But as Pavel said earlier on, outliers are okay if they're justified by the data. So if you've got density for a side chain and it fits great and it shows up as a Ramachandran outlier, okay, great. You've got a way to justify that in a paper. If you've got no density there and you put that residue there, hopefully a reviewer would say, why? That's not right. Yeah. And so keep it clear in your head. An outlier doesn't mean an error. An outlier just means something that doesn't conform to what we expect. Yeah, so outliers are allowed if you can prove that they're real. Same idea with rotamers. We know by analysis of protein data bank structures that side chains adopt specific conformations typically. And you can actually plot these in terms of this is chi1 versus chi2, the angles going along the side chain. And you can then validate a model against those distributions. Again, is this good? It's not so good, right? There's a whole bunch of points here that don't fall near any of those peaks. And you typically expect maybe up to 1% of a structure, maybe outliers. Again, though, you'd want to be justifying them, right? If there's no density, there's no justification for it to be an outlier. So you mentioned hydrogens a minute ago. If you think about it, a macromolecule, about 50% of the atoms are hydrogens. Now, what is less clear is that most of the contacts between atoms are actually hydrogens packing with other hydrogens or other atoms. So a lot of the contacts in a structure really are hydrogens involved. Now in X-ray crystallography, we pretend hydrogens don't exist because we don't see them experimentally, but they are really there. You didn't somehow make a protein that had no hydrogens, right? If you did, it would be a very strange protein. So the Richardsons actually pioneered the idea of using hydrogens to calculate packing more accurately. Because typically we don't use them in our refinements. If you put the hydrogens on at the end of the refinement, then see how the hydrogens pack with other things, you get some idea about where things aren't really packing very well. So this quality of packing and what kinds of clashes we're getting between hydrogens and other atoms is actually a very useful thing to use. So the idea here very quickly is that you make a surface around all of the atoms by rolling a ball, very small ball, around the atoms. And then you look at where things overlap between atoms. So in red, that's where some atoms overlap too much. Yeah? So that's what's called a clash. And you can see there's a hydrogen that's too close to that other atom, carbon probably there. This place here is where you've got a nice, it's green because you've got a nice just touching of atoms here. So that's a nice contact between things. And then this place here, we've got overlapping points, but that's because this is a hydrogen bond, and this hydrogen, of course, is pulled closer to this oxygen. So that's a favorable interaction. So the kind of analysis that's done in Molprobity is to sort of make these surfaces and look at how points overlap, and then report to you and say these atoms are too close, for example. So if you use the Molprobity web server, you can put your structure in here, and it will show you things about. So the clash score really counts how many overlaps there are per so many residues, and then we'll convert that into a percentile score as to how good the model is. And second percentile, that's not a good thing. You want to be in the 100th percentile. Yeah. So second percentile means you're pretty much bottom of the class, and that corresponds to a very low resolution structure. But you can see there's also reporting on Ramachandran outliers, things like that. And just so you know, Molprobity will give you this Molprobity score, which here is 4.55. That approximately is equivalent to the resolution of this structure. So if you look at structures in the protein data bank, this is equivalent to a structure that's been solved and refined at 4.5. So and if this was a 2 angstrom structure, I'd be kind of worried, right? So why does my model look so much like a low resolution structure? It means I've done something very bad with the geometry. And you get a list of outliers. You can go and, or problems in terms of clashes, you can go and fix. That's the Molprobity website in Phenix, and we'll see this in the tutorials. You can do the same thing. You get a list of all these outliers. You can click on buttons. You can go and fix them in Qt. But we'll look at more of that tomorrow, so I won't say any more about that. So hopefully the thing you can be convinced about if you don't practice this already is that using validation tools throughout the process of solving a structure is going to be good for you and make life easier. So this isn't, this is a structure. These are two structures solved, similar resolutions. These purple places are where there are all the clashes between atoms. The green things are Ramachandran outliers. The gold things are Rotemer outliers. If you don't apply validation, you can, even at this resolution, you can end up with something like this, relatively straightforwardly. Whereas if you do apply validation, you can get a model like this, where there are no bad clashes. There's one Ramachandran outlier and a couple of Rotemer outliers. That's, for this resolution, that's very, very reasonable. But the thing to do is to use that validation very early on to avoid introducing errors into the structure, which are then difficult to get out if you don't fix them. Yeah, it's very bad if you introduce errors, do refinement, then it can be difficult to find those errors later on and fix them. And just to show that using validation is generally a good thing. This was something they did at the Southeast Structural Genomics Center a few years ago now. So that group really used these validation kind of tools throughout the process of doing their crystallography. And these graphs just show in green their results compared to the average results from other people putting structures in the PDB around the same time, shown in blue, for example. Shown in gray. The blue ones are control structures done by this group where they didn't use the validation metrics. And what you can see is that if you use validation, you will end up at the end of the day with consistently less Rotemer outliers, less Ramachandran outliers, on an average, an improved R3 as well. You get better models at the end of the day. So validation is something that is becoming increasingly an issue in structural biology. The PDB has established several task forces to investigate validation in crystallography, in cryo-EM, a number of different areas. The crystallography, we were the first people to engage in this, so we developed, a bunch of us came up with a set of guidelines. So now if you go to the protein data bank, you will see, I hope, that for every structure, there is a little bit of information that talks about validation of this model. Yeah? And it's a very quick way for somebody to look and say, oh, this kind of looks good, looks better than the other structure that's this resolution. Yeah. So essentially, every structure now will have a lot more information that says how good it is, how reasonable it is. And those will be hopefully very useful things to you if you use a structure from the PDB. If you go and use somebody's structure from molecular replacement, if you've got two choices and one looks better with the validation, you'd probably take the better validated one, yeah? And, you know, of course, you don't want to put stuff in the PDB and have everybody see that you've done a crappy job, I hope, right? Because, you know, people remember your name and say, don't get structures from that person. So just to summarize, you know, validation is a vital thing. I mean, it's a vital thing in doing science in general, but it's sometimes a bit easy to get wrapped up in the process of something like crystallography, that you just follow the recipes and assume you get the right answer. No, don't do that. Validation is important. You have to be critical all the time. And really, validation is common sense at the end of the day. And it doesn't just start with models. I told you about models, but it starts with data. You need to validate your data and understand whether your data is good or bad before you start doing anything. If we have time tomorrow, we could talk more about that. And you have to be critical about things. Does the model fit all the things that I know? And again, I'd reiterate, I would take a bunch of biochemistry as more reliable than a single structure. I'm a biochemist originally, so you know, that's maybe why I say that, but really, a bunch of different experiments by different people in different labs, if they're all consistent and yours is not consistent with that at all, you've probably done something wrong. And you should be open to everything, right? You should not assume, but you should be open to the fact that something has gone wrong along the way. This idea, I think maybe Tom mentioned it earlier on, you know, your space group assignment, you can never really be 100% sure about that. You can have a hypothesis about it, and you'll be more and more sure as you go through the process, but you should always be willing to accept the fact that it needs to change. And, you know, this quote from Feynman, but, you know, the first principle is that you must not fool yourself, because you're the easiest person to fool, right? You would like to have an answer. Don't fall into that. You have to think critically about what you're doing. Okay, so I'll finish there, and again, thank all the people involved in Phenix, especially in this particular context, the Richardsons, because they've done a lot of this work in validation. So, any questions?
Can you comment on refining with protons, and particularly when you have a ligand? Is it always a good idea to add the protons?
So,
Resolution way you should add refine with protons?
well, so there's two aspects to this. So there is clearly, if you include a better description of the chemistry by adding the hydrogens, it's going to do a better job in refinement in terms of geometry. So that's generally a good thing. The other side of it is that it actually also impacts the R factors as well, because the people tend to think that hydrogens only scatter at high resolution for some reason. I guess it's because it's only when we have high resolution that we see them. But really, hydrogens only scatter at low resolution. So at any resolution, if you include the hydrogens in your model, you typically will improve the R factors because you're adding an additional contribution to the scattering that should be there. So generally, it's a good thing. I mean, there's a question of when to do this. Probably not early on in the early stages of refinement, but as you get further on and you think you have a model that's close to being kind of right, adding those hydrogens should be a good thing. Now, technically, trying to do that at 4 angstrom, you know, the results in terms of what happens, I think probably we need to work on that to make that better. But, you know, conceptually, really, you should be able to include them, and you should include them at any resolution. Because it's chemistry that we're not including in the model, right? So it can't be a good thing to miss out chemistry. But practically, the advice would be, think about doing it later on, as you get towards the later stages of solving a structure. If it improves things, which it should in terms of R factors, free R factors, and geometry, sure, do it.
And the PDB would you then deposit with the protein?
Well, that's I would say that's a philosophical argument to some degree. My perspective is, I've gone to the trouble to make a model. Why wouldn't I give everybody that model that I've made? And that includes the hydrogens. Some people say, well, you can recalculate those hydrogens. It's straightforward to say where they all are. That's not our experience. It's actually you can get a lot of them from the positions of the heavy atoms, but some things is very difficult to predict. So I'd rather just give somebody the thing that I've made, and if they choose to delete the hydrogens, that's fine. They can get rid of them, but if I don't put them in, they're not going to have them. Yeah.
You also have the argument about what length to use for the hydrogens as opposed to the center, atomic center versus sort of X-ray.
Well, so yeah, that's a good point. In Phenix, we use the electron cloud distribution for the positions of where they are, because that's where the scattering is from, except if it's a neutron experiment, and then we use the neutron length. So we actually do use different lengths depending on the experiment.
Right, there's a potential for confusion for people downloading the structure and seeing the hydrogens at those positions.
Potentially, yes. And I saw a paper recently where, well, yeah, I talk about that offline, but I think I've seen a paper recently where somebody actually really didn't understand what goes on in a crystallographic experiment and got a confusion around that. But I still think, again, people have the choice to delete things if they're not sure. And yeah, if you're doing molecular dynamics, you use neutron, nuclear lengths in their simulations. I don't think they would take our hydrogens as gospel, or I'd be surprised if they did. Right.
Yeah, I think the experts are always going to know how to treat it. It's the people who are just occasionally using the structures that are
Right.
stumble.
But I think they will stumble either way, actually, if they're there or not there, because they won't know what to do either. So,
Yeah,
yeah, I'd rather say I'd prefer to personally err on being, more inclusive and giving more stuff generally. And there is a fallacy that the PDB will reject your hydrogens or your structure if it has hydrogens. Not true. They will take your hydrogens.
I don't know. I would.
No, people say that the PDB doesn't like hydrogens and they delete them, and they don't. They don't. If you want them there, you can keep them. Okay. Thank you. So we will see you guys tomorrow morning, back over there, I guess, to do more tutorials.